Hello everyone and welcome to another Minitab episode of Fun Times in Statistics. As you can see, I've got the Inference for Linear Regression data and document opened for this little adventure we're going to go on today. Please don't forget that these will be found above our current this video. Well, there'll be the Minitab 18 video above this and then this one. So this description goes with Minitab 18. Some of these are in the exact same spots, so it's not going to be a huge difference when it comes to our output. It's just a matter of making sure you click the right button. So to get some practice in on this, a lot of the stuff we're going to do today relies on you using some of your skills from linear regression and last time. So, just keep that in mind. So you're going to see me do some stuff that, is new, and some of it will look a lot like last week because this is a continuation of last week. Anyway, this is my second time recording this video. Hopefully this time it won't crash in the middle of it. Let's be hopeful. So what we have here is some data on some older tablets. I believe the newest one in here is from 2012, forgive me. But what we have here is the video battery life in hours and the maximum brightness of the screen. The idea is they took the these tablets and then turned them on their maximum brightest setting and ran video on them until they died. So that's what video battery life represents. And they recorded the screen brightness in coulombs per meter squared, because that's a really common unit of measurement. Anyway, no, it's candles. Candles per meter squared, which is how you measure brightness. Fun fact. Well, one of the ways. So we're going to check some assumptions and conditions for linear regression and inference. I'm not going to be checking independence today, simply because that's when you should check by looking at the data itself and asking about your sampling stuff, so I'm not going to be doing that. But I will be checking for nearly normal and linearity real quick. So to do that, I'm going to go up to regression, then to simple regression. And as I've said, I want to predict battery life using brightness. Now I'm not going to change this from linear because, well, I want to see it, well, we're hoping to see a linear model, but I do want to check some of my options. Specifically, I want to go check out some of my graphs. Now in Express, you're not going to be able to choose which residual plots you're going to be looking at, so we're just going to be looking at all of them. So we're going to look at versus fit, versus order, normal probability, and the histogram. So we're going to be checking our nearly normal condition using these. Let's go ahead and hit OK. There she goes. Where's my graphs? There they are. So there's the fitted line plot, so you can take a look at this. I'm hoping you notice that it does have a sort of linear shape, but it appears to have a lot of scatter. Anyway, so in response to what we're seeing, I only look at order if order matters. Here, since it's just brightness and video battery life, the order in which they occur has no element of interest to us. If it was something that happened over time, then yes, I would definitely keep track of that. Here's what I'm looking for. Does this look nearly normal? It appears that most of my dots are close to the red line, so I'd go ahead and call that nearly normal. Or if you want to, you can look at the histogram and ask yourself, does it look like it's unimodal, symmetric, and or has a relative bell shape? In this case, it appears to have some skew to it, which isn't too surprising. It's not perfectly normal up here on the graph. It does have some wiggles away from being straight, but it is straight enough to where I'm going to go ahead and call it okay. So as far as nearly normal goes, woohoo, appears to be satisfied. Based on the normal probability plot. Okay, nearly normal. We're not very satisfied if we can't spell satisfied correctly. The other thing is, looking at the histogram, you could say this appears to be unimodal, which is all you really need to have this be nearly normal. So I'm going to copy this one over and paste it. Oops. I'm using Command C and Command V to copy things in case you don't know the hotkeys on your Mac. The Command button is the one that looks like a square with a bunch of little circles on each corner. Anyway, so since I've got the histogram on here, I really should talk about it too. So since the histogram is unimodal, I don't want to say data, the residuals are normal enough for to meet the nearly normal condition. Okay. Let's go ahead and grab that one. Where is it? There she is. So I'm checking my residuals right here. Copy and paste this over. Paste. I'm going to pause this because my husband has decided to vacuum. Okay, so what we're looking for here is we want to see equal spread. So about an equal number of points above the line of 0 and below the line of 0 to indicate equal spread. The other thing we want to see is we don't want to see any patterns or any type of like structure. It needs to look random. And this one looks nice and random. This is exactly what we want to see. So we're going to say that this meets the equal spread condition because of the things we just said. The number of points. Is this recording? Yeah, it is. Okay. Above and below 0 are about equal. And there is no patterns. I have a hard time with the word patterns because it sounds like it has a U in it to me. Or unusual values. Okay, cool. Next up, we are going to need some values from the output. So I'm going to scroll this up just a little bit. Hopefully you've got that down. If not, that's okay. You can pause the video and resume in a minute. Cool. So I'm going to get... Is that everything I need up there on the screen? I think so. I wish I could zoom this in a little better. Anyway, so next up, I want to find the residual standard deviation. This is also known as the standard deviation of the residuals. This is also known as SE or just S. So as you can see, I've positioned it onto my screen already. That's the value of S, which is in your model summary, and it is 1.94581. So in case you were missing where I got that from, that's from the model summary box. I'm going to go ahead and copy that box over just so you guys can see where it came from. So it's this value right here. So that's how spread my residuals are. Now when you're looking at comparing as to whether or not it's a good spread or a bad spread, or is it spread too much, because remember this is a measure of error, and is my model good? What you want to look for is you want to compare S's size to your prediction. So the thing you are predicting, also known as your response variable. So I want to compare this to battery life. So be thinking about this in terms of hours of battery life. So this is saying that your error is off by possibly up to 2 hours of battery life. And then looking at some of your battery life, some of them are pretty close, well, like all of them are pretty close in size to 2. That's not good. Now, if this was like a half an hour, I would be real happy. That would mean I may be off by a half an hour in my predictions. This says on average I'm off by 2 hours. That's not good. That means that this is a bad model. The other thing you want to look at is your R-squared value. Oh my God, is it horrible? But that shouldn't be too shocking. Like going back and looking at the graph of the linear model, there's quite a bit of spread here. So we're not going to be too surprised that this is a bad model. And if I never showed you any bad models, I really wouldn't be doing my job, just in case that's unclear. Okay, now the next up thing is find the value. All right, find R-squared and then tell me what R-squared meaning is. I kind of just did this, but here we go. So R-squared is 4.82%, which is not good, but I specifically want to write what this means, okay? So what this tells us is about 4.82% of the variation or changes seen in video battery life can be explained by its relationship. That's not the right its. With maximum screen brightness. I'm going to use max instead of maximum because I'm already tired of typing. Which clearly isn't much. I mean, it explains almost nothing. It's not even 5%. Hopefully you look at that and you're like, okay, clearly bad model. All right, I need to do some fixing on this. Okay. Next up, we want to find the standard error of the regression slope. Now, I have a bunch of standard errors on here, so I want to be clear which one you are using. Hopefully, you remember from the coefficients box menu what you should be reading off of it. The constant, that's what's creating your y-intercept, and the value of the y-intercept is right here, the coefficient value. And then maximum screen brightness, since that's our x variable, or our predictor variable, this value, coefficient, is the slope. And so if I'm looking for how spread or what is the standard error of the slope, I'm looking right next to it at the standard error for that coefficient. So rather simply, I'm going to copy this box over, boom, highlight the value that I want, and then I'm going to write the symbols behind this. So you may remember standard error for the slope and what it is, but just in case you don't, here it is again. It's the standard error of B1, because remember B1 means the slope, and that's 0.002639. Cool. So now that I have all of this information, I can perform the hypothesis test about whether or not the screen brightness is well predicted, the battery life is well predicted by screen brightness. So let's set up our ho and our ha. So remember, you should be using beta for this, which I don't know, on a Mac, is it easy to insert a symbol? Let's find out. What did I do? Oh, I got rid of that. Oops. Advanced symbols. I don't remember how to do this. It's a good day when you remember things. Oh, and now I've got the swirling colors of death. Nope. And now the tiniest symbols ever. Okay. Insert. Did that go okay? Let's close this. It went okay, yay! So remember, beta is the line for true slope. If what you want to think about beta as is, this is the slope if I had all possible tablets and all of their video battery lives and all their screen brightnesses, rather than just a sample of, I think there's 200 tablets in this data set. So, and we always test our alternative and null for this as being equal to and not equal to, and I close this and I need a not equal to now, which is awesome. Which I have no idea where the not equal to is on here. Aha! It has been found. Insert. I probably put it in the wrong spot. Okay. I should have did this ahead of time. Cool. So if anything, your ho and your ha for the null and alternative hypothesis for the t-test and what you're doing when you're testing slope is always the same. This is going to be interpreted as, oh, my true slope is nothing, or there's no linear relationship here. It's not meaningful to try to use maximum brightness to predict video battery life, and the alternative is, oh, it is not zero, so it means something. This describes something about how the two are related. So next is find the t-statistic and the p-value, rather simply, since I'm testing slope, and my slope is this second row right here, or last row, I guess is the way you could say it. Here is your test statistic and your p-value. Or sorry, yeah, test statistic and p-value. I'm going to highlight this in a different color. So my test statistic, which is a t in this case, is 1.84, which is not very big, so you shouldn't be too surprised when your p-value is also, it's close to being small, which I was surprised about, which means it's close to having some meaning, but not enough for it to matter if you look at the r-squared value. So keep this in mind. This is just a good practice when it comes to, you know, when you're evaluating some results you get from a statistic. You know, just because it's meaningful and has significance doesn't mean it's practical. So in this case, even if it came out significant, I'd be like, yeah, but it only predicts like 4%, so what good is this? I really should be looking at something else. Anyway. So hopefully you look at this p and you're like, ooh, it's bigger than alpha, which means I am going to be failing to reject that ho. Because it's a big P, although not a very big one. Anyway, so you want to look at this and you want to state your conclusion. Aha! My slope appears to mean nothing. There is not a significant linear relationship between maximum screen brightness and video battery life. There is significant evidence that there is not a linear relationship, or at least a meaningful one, between video battery life and max screen brightness. I bet you there's plenty of other things that cause your your video battery life to go worse. Like, how about just how many pixels per square inch you have? Like, that's got to be more important than brightness. Anyway, let's do the next one. What's the equation for linear regression? Well, it's right here. Let's just copy this because this is an easy question. And that's the easiest place to grab it for on a Mac either. It's just right below your model summary, or sorry, your coefficient box every time. Okay. Now we need to find the 95% confidence interval for the true slope of the line. This was the part I told you you absolutely have to do by hand. There is no way to do this one with using technology. Minitab will not do it for you. So I'm going to pull up my calculator. Is this it? Yep, there it is. And I'm going to put this off to the side because I'm going to need it in a second. Oh, there's no good place to put it on a Mac. Hold on, let me pause this for a second and move some things around. Okay, let's get this party started. So to do the 95% confidence interval for the true line of the slope, we're going to be using the slope, B1, plus or minus a t-value, which we'll get in a second, times the standard error of the slope, B1. Oh, and it capitalized my B1 on me. Way to go, Word. I swear, you're like on a mission to annoy. So some of these values we know already. We know the value B1, we just used it. It's the value of the slope, which is right here in your regression equation. So I'm just going to steal that real quick, like literally, because, you know, I can copy and paste it over here. Then we have our plus or minus, which I'm writing kind of weird, but hopefully you got it and it's okay. And then I need my standard error for the slope, which we found earlier. So I'm just going to go steal it from up here. Cool. And then I need my t-value to multiply it by, right? Which, oh, that looks like just a mess. Let's use the format painter to like make it all match because I like it better when it all looks the same. Okay, cool. So hopefully you remember how to get a t-value off of Minitab Express, but if you don't, I'm about to do it, so it's good time. It's important to note we're going to do a 95% confidence interval. So at this stage, what I really need is my degrees of freedom. So my degrees of freedom for linear regression, since I have two variables involved, is always my sample size minus 2. Normally it would be -1 for a one variable, but again, we're doing two variables. We have screen brightness and we have video battery life. So if you scroll through this or count the number of tablets on here, it's actually 69. Fun fact. Notice the total is 1 less than that, and the error is 2 less than that. So if you always just look at the errors degrees of freedom, it's always correct. It's the one you actually want from the analysis of variance box. So we're going to be using degrees of freedom of 67. So we're going to go up to probability, distribution plot. We're going to select display probability. Let me do that again because that went by really quickly. So probability, distribution plot, display probability. We are dealing with a t, not a normal. We have a degrees of freedom of 67. Woohoo! And we want to, oh no, we want probability. Oops, I switched that. And then I want to put in my tails 5%. I want 95% in the middle, and it'll split it for me using equal tails, which is exactly what I want. Let's hit OK. And there is my t. So I'm going to use quite a few decimal places on this because this is quite small. 1.99, well, let's do 6. I got lazy. Cool. So at this point, you pull out your calculator. Life is good. So here you see the keypad of the calculator. This should match the screen if you have a TI-84. So I have 0.00486. I'm not adding plus nothing. You can't make me. Minus, and I'm going to use a set of parentheses here. I know I said I'm not going to round. I probably shouldn't just because, you know, things. And then enter. Da-da-da-da, super tiny. Good job being a small confidence interval. Oh boy. So, oh, I gotta move this over just enough to where I could see it. Hold on. Yoink. So, -4 power. Okay, so that means move the decimal place 4 places to get this. So, 3 zeros in front, and then 1 more to get to the 4. 0, 7, 4, 4, 4. Cool. And now I'm going to cheat. You can see how it has this little tiny entry button, unit second entry, and that'll bring up the last thing I entered. And then I can arrow over like 8,000 times until you see that negative. And Come on, one more over. There we go. Change that to a plus, and then hit enter again, and that'll give me the upper part of the interval. Put a little space there. 0.1012 7 and some stuff. Okay, that's another thing. I missed the negative on that first end of the interval. And that's important because that means 0 is the interval, which means my slope could be nothing, and that's exactly why earlier when we were doing the hypothesis test, we were unable to reject the idea that the slope was nothing, because clearly the confidence interval supports that as well, which is good. Woohoo! So this tells me my slope means that either, you know, as I increase maximum brightness, it will increase battery life by 0.1, or it might decrease it by a tiny amount. Clearly is not having an important effect. But that doesn't matter because we're still going to use it to do some confidence intervals and prediction intervals for specific values. So just to remind yourself, confidence intervals for a value will predict different things. This predicts the possible values, the mean of video battery life for a specific screen brightness. So if I looked at all tablets with a screen brightness of 800 candles per meter, sorry, not 800, 500 candles per meter, this will give the average battery life possibility for that specific type of laptop. Sorry, I keep saying that, tablet. And then the prediction interval will give the range. So it does the same thing, but for the range. It gives the interval for the possible range of the value. So if you had a tablet with this specific maximum screen brightness, what you could use this for is to ask yourself, am I close to average with my video battery life? Am I within the possible range? And if not, well then you've got a bad tablet. You should probably ask for a refund and or, you know, take it back and stuffs. So let's use this on Minitab Express. So these two had horrible formulas. I don't know if you remember this from the notes, but they were specifically scary, but they're very easy to do on Minitab Express. So we're going to go up to regression. So you'll notice that when I hit this button, there are some things that are dark that were not dark before. We are making predictions, so we are going to be using predict for regression. Now, in order to use this menu, you have to have already ran a linear regression. You can't just use it flat out with nothing going previously or without any data. So you notice how there's this green check over on the top of C2? That's what tells you you're going to be able to use this. So we're going to hit predict for regression. And it's going to ask you, well, what video battery life are we going to get? Well, for our response, what maximum brightness do we want to do? I want to do 500. And you can put multiple values in here, so if you want to have like 3 or 4 of these you want to check, you can do it all at once. Always check your options. Since I'm doing 95% for both of these and two-sided, this is set correctly. And then we're going to go ahead and hit OK. And there's our 2 intervals. Okay, so a couple things what we're seeing. So it's telling you you're inputting 50, oh my gosh, 500, and then it gives you the prediction. So where this comes from is if you would have placed 500 into the line itself that it did, the regression line equation right here, this is the value it would have gotten for the fit. So this is also kind of a fast way to get a value if you just need one. Anyway, so right here we have the confidence interval, which do I have an option to just copy that part? No, I don't. That's awesome. Yep. I'm just going to type it real quick. So 7.7375, comma, space. I am now reading what I'm typing. Never again. Okay, so that means the average, sorry, predicted average screen brightness for a tablet. No, it's not screen brightness we're predicting, it's battery life. $500 candles per meter squared screen brightness is between 7.7375 and 9.5448 hours, and I forgot how confident I am. Ready? We are 95% confident that the okay, so what does this mean? This means that if, say, your tablet happened to have a screen brightness on average of about, you know, 8 screen hours when it's turned up on max, that, I mean, you would be close to average, so that would be good. I mean, you'd be between these values and you'd be pretty sure you're good. Now, that being said, if you happen to have a tablet with only like 7 hours that it would last for its battery life when you had it on full brightness of the screen and running videos on it, you should look at this and be like, okay, so I'm just a little below average. That's fine. It just means you're below average. That might not mean anything. So that's not as useful here. However, let's take a look at number 9. What we're going to do now is we're going to use the prediction interval. So this is the range of possibilities. So remember, the prediction interval gives you a range, not an average. 6535 12.6287. Cool. So this means that we are 95% confident that the range of battery, so it's not average, be careful, no average in here, screen battery life for tablets with a screen brightness of 500, keep writing 550 on accident, candles per meter squared is between, let's do 4.6 and 6.5 and 12 point, I just realized I missed that decimal, 6.3 hours, because that's what our time unit is in. Okay, so in looking at this, I want you to think about my example before, like 7 hours. It's within the range. That's perfectly reasonable. It's exactly where it should be. Now, if you did this and your tablet happened to do like 4 hours, you should be like, ooh, well, that's not good. That's really below range. Or it could be just the 5% chance that it's, you know, not accurate with our confidence interval. So be careful with that. But the range is important. So one of the most frequent ways this gets used is when it comes to the pricing of objects. So having the range of possible price values of what you might sell your product for on at different stores with different markups is very important. So if somebody's not within the range, you know they're doing bad things. And also knowing what the average possibly could be would be very important for pricing as well, because then you know if somebody's close to where they should be on average. So these are important predictions when it comes to pricing models. I'm hoping that helps those of you who are interested in that kind of thing. If not, well, I'm sorry that we did this. That's the most common application of this, but there are many others, like look at what I'm doing with tablets. Let's do this last one. This is more or less just for fun, and so you can see the prediction and the confidence interval for a specific value in a visual way for those of you who are visual learners. So I'm going to create a scatter plot that displays the confidence interval for the predicted mean values in the prediction interval. So I'm going to create a picture of the two we just did in 8 and 9. Okay, so this, again, just a visual. I'm going to leave these two up here because I'm going to show you something on them in a second. So to do this, I just need to redo my regression model and have it produce that graph for me. So I'm going to click up here to the regression model we did at the beginning. I'm going to click Make Similar, so that it's got my X and Y in the right spot. I'm going to click over to Options, and I'm going to check these two boxes, Display Confidence Interval and Display Prediction Interval. So it's just going to display it on the graph for me. Let's go ahead and hit OK. It doesn't look like I did anything, but we're going to scroll down and you'll have a new graph you haven't seen before. So I'm going to copy this over so I can make it a little bit bigger on the Word document, and we can talk about what this is doing. And I specifically want it so we can see it next to the thing I have above it. So the red line, as you may know, is our linear regression line. The green line is our confidence intervals. Remember, this is the one that's predicting the mean. And so as you look at this, the green bands make the upper and lower part of the confidence interval. So we did 500. So if you look at 500, the range of it appears to be about from, well, let's see if I can do this accurately and moving over. Looks like it's either a little bit below 8. Yeah, a little bit below 8 to like almost 10, and then look back up at your interval for your confidence interval for 500. Oh look, it's like 7, almost 8, and then 9.5-ish. Hopefully that makes a connection for you of what's happening here. So these widths represent individual confidence intervals for specific values. And then the same thing for the prediction interval. So notice this goes over the range of all possible values, going from down here to up here. So for instance, if I do the 500 one, it looks like the 500 one is about at a little bit above 4 to, this is so hard to do with a mouse, a little bit above 12, almost 13, which is exactly where this is at. So we're good. Hopefully you're seeing that that's where this is coming from and where these intervals are being made from. The other thing I want you to notice is, remember, the PI, the prediction interval, gives you the range prediction, the prediction of all possible values going from minimum to maximum for these individual different brightnesses. So in looking at your scatter plot of all your different blue points on there, you hopefully notice that there are 3 outside of those purple bands, and if you do 5% of 69, which is the number of tablets in this data, you'll notice that it's really close to 3. So I predicted 95% of the data. 95% of the data is within there, so that's good. The other thing to notice is that it is closer as you head towards the center of this graph, because remember, the green lines represent the average. They're a little more accurate the closer they actually become to the average. So when it's near the center, or the average, the CIs for specific values are more accurate, or tighter, or more precise, you might say, than they would be on the edges. So just to give you an idea of what this looks like and what it's up to, I hope that that helped you understand a little bit more about linear regression and how you can apply inference to it. Have a good day.